welcome to the first day of May and the last day of the week for week 15. I'm going to talk just a little bit today about presentations, then I'm going to move on to the extra credit, and then I'm going to go over a little bit of ANOVA. So let's start with presentations. Many folks have already started to either send things to me or have inquired about the assignment, and just to let everybody know, as a reminder, that the presentation, which generally we would be doing next week in front of the class, obviously is not going to happen. So the materials that I've given you to look at, or at least the structure I've given you to follow, involves you, of course, as you would any other way, come up with your own scenario, generating your own data, and then applying either chi-square or correlation to the fact pattern that you generate. And again, I think I need to just continue to emphasize that when I say generate your own data, whatever fact pattern you come up with, if we're talking about days, number of days, scores on tests, scores on depression or anxiety indexes, I mean, you might as well throw darts at a board and record the numbers you find. It's not that important as long as you do as long as you create the fact pattern originally and you apply the mathematics correctly and come up with an answer and answer the questions about the null hypothesis, the calculated value, degrees of freedom, critical value, the outcome questions about the p-value. That's mainly it. But this really is a synthesis exercise. It really is asking you to take a look at what you've learned and put it in a creative way. So it's part application of things I've taught you, but it's also creative as well. So it really is a synthesis. Again, if you have any questions over the next week, folks have even said, well, can you give this a look and see if I'm kind of on the right path? Sure, no problem. I've been doing that with your homework all along. So it's really not a problem for me to do that. Again, to me, the most crucial part is you're coming up with this stuff yourself and you're applying the formulas correctly to the fact patterns and answering the questions completely. That's really it. Now, remember, just as a reminder, presentations are worth 30 points and they're worth 10% of your grade. So, I mean, it's a good assignment. It's not going to topple anyone over. It's not like it's a exam or a homework assignment, but still, it is important, and I think it's worth your time to complete it. So that's kind of where I'm at with that. With respect to extra credit, again, I've sent out the fact patterns, and unlike the presentation, with the extra credit, I've given you the data to analyze, and I'm asking you to do it on the Excel. So again, I've taught in previous lessons how to use Excel to figure out answers for both chi-square and correlations. And again, you're following my pattern there. But it's really not hard. It's just a matter of taking the time to do it, answering the questions. And I do ask you to take a screenshot. And again, you can do that a number of ways. Some people have even just taken a picture on their phone of the screen. That's fine. You can also use the snipping tool for Microsoft. And I'm not really sure how you bring it up in Mac, any kind of iProduct, but I sure know how to do it with, in fact, I could probably even show you how to do it here. If you're trying to take a screenshot, all you have to do is go down to this little box right here and type in snip, and then you're going to see snipping tool. If you click on snipping tool, whatever screen you have in front of you, you can go ahead and hit mode, and you can say full screen snip. And when you do, it basically just takes a snapshot of the whole thing. You can see that now. I'm not going to save this. I'm not going to save this. I'm just showing you how easy it is. And then after you've saved it on, say, your desktop or whatever, you can immediately send it via email as an image or whatever. So with respect to presentations, I hope I've been clear. I feel like I've tried to give you as much as I can with respect to support. I think I've handed out the I think I've handed out the instructions every way but through mail. I feel like I've sent it as many ways as I can. Same with the extra credit. It's on Canvas. It's in announcements. It's I feel like I've sent it everything but paper airplanes to people. So I feel like I've given quite a bit of information and guidance here. So, but nonetheless, if there's still some confusion and if there's still some questions, that's fine too. I don't think that I'm going to have any trouble over the next week finding time to help you if you need it. That being said, the last part today, ANOVA, I decided, of course, this week I was not going to give you a participation quiz like I do at the end of each week because you had quite a bit going on. But generally, I do give a participation quiz in the last week or two, just to kind of sew up the semester. ANOVA is something that I like to end the semester with if I can, and it's not going to appear on any test at all with respect to we have no more exams left except the optional, and that's really what I'm talking about here. The optional exam will not include ANOVA. Let me repeat. The optional exam number 4, which you could use to replace a score from a previous exam or a missed exam altogether, will not contain ANOVA. The only thing I was thinking about putting ANOVA on, which I've done just about every year, is on a participation quiz, which would be at the end of next week, like we've always done our participation quizzes. And that's the only thing I can think of to do with that. And again, the basic knowledge of ANOVA is not anything that's going to include any kind of calculations. We're way deep and too far into the semester to do anything like that. You need to be doing your participation and extra credit if you're going to do it. But if you do, but if we do have a participation quiz like we have at every single week of the semester except this one, and of course spring break, I don't think that's going to break anyone's back. So I'm going to proceed with teaching a little bit about ANOVAs just so you can distinguish them in the future. It very well could be that in your in your social work 111 research courses, anything you might do as a master's level student, it's good to at least know what an ANOVA is. I mean, that's just to have the basic general knowledge of what an ANOVA is worth, I think, our time. So that's really the only reason that I'm going to be spending any time with ANOVAs. So I hope that this was fairly clear as a beginning, and I'm going to go ahead now and shift into talking a little bit about ANOVAs. So continue with me. And now I'm back with the PowerPoint presentation I'd like to use for ANOVA. First thing to point out to you is that ANOVA is not just ANOVA, it's actually shorthand or an abbreviation of a longer term, which is analysis of variance. So that's the first thing. So when you hear the term ANOVA, and there are different kinds of ANOVAs, know that we're not just saying ANOVA just for the sake of ANOVA. It's a shortened version of analysis of variance. Now, this is what occurs in Chapter 11 of our text. Hopefully you'll get a chance to look at it. I mean, I'm sure you got lots to do over the last week or so, but if you get a chance to glance at it, again, I'm not going to go real heavy here. We're not doing a lot of analysis. I just want you to know what it is and why it's different from, say, a t-test. So that's where I'm kind of going with this presentation. I have for you first a little bit of a introduction, and I want you to follow this the best you can. Let me read this to you. The reasoning behind analysis of variance is as follows. If two or more populations have identical averages, let me just stop there. Think of identical averages among populations, and notice it didn't say samples. It said the actual, like the mu of populations. Then the averages of random samples selected from those populations ought to be fairly similar as well. So What's that saying? That's saying that if you have populations that are similar, the samples that are coming out of them should likewise be similar. But keep going. The sample averages probably wouldn't be identical because of sampling fluctuations. In other words, no two samples are exactly the same. That goes without saying. You know that sample statistics vary from one sample to the next and are rarely equal in value to their corresponding population parameters. You remember what parameters are, okay? So again, when we're talking about population parameters, the samples that are coming out should be close, okay, especially if the samples are large enough. However, large differences among sample averages would cause us to question the hypothesis that the samples were selected from populations with identical averages. So it's kind of like as above, so below, or as below, so above. If you've got samples that are widely varying over time, then you might start to question whether or not the averages of the population's mu's are identical either. Okay, I can draw some pictures of this in a minute, but nonetheless, this is kind of where this is all going. Next one is this. I like this because it sums up very nicely why we would bother using a t-test. I'm sorry, an ANOVA over a t-test. In general, researchers use the t-test if they have two groups. Remember how I used to say, think of t-test as two groups, okay? And ANOVA for three or more groups, because using multiple t-tests will increase the odds of having a type 1 error. Now, I don't know if you remember this right, but if you don't, I'm going to remind you, a type 1 error is where we have effectively rejected a null hypothesis that we should have accepted. We got it wrong. We rejected a null hypothesis we should have accepted. That's the definition of a type 1 error. Last one. Thus, ANOVA has three definite advantages over separate t-tests. Instead of running a bunch of different t-tests, which would mess everything up, you're just going to run an ANOVA. It yields an accurate and known type 1 error probability, whereas the actual alpha, which would be like a 0.05, okay, for the set of several separate t-tests is high, yet undetermined. 2, it is more powerful when alpha is held constant. That is, if the null is false, it is more likely to be rejected. So we're not going to have as high of a type 1 error when using an ANOVA than if we were using a bunch of t-tests. Okay? And then finally, it can assess the effects of two or more independent variables simultaneously. Effectively, ANOVA is a flexible vehicle for testing averages when you have more than two groups and you're trying to figure out whether or not they're similar or different. You're testing again for differences. Here's the basic information. ANOVA is an inferential statistic. Absolutely. Like t-test, it contains nominal and interval ratio levels of measurement. Okay, so it is like a bigger t-test. Okay, and now you're going to know why in a few minutes. However, unlike t-test, three or more samples are analyzed. Okay, I've been over that a few times. Okay. We measure ANOVA with an F ratio or an F statistic. So again, F seems to be, well, doesn't seem to be, it is the identifier for a ANOVA. So remember when we were doing chi-square and we had the x square, and that's the symbol for chi-square. Remember we were doing correlations just recently, the R, Pearson's R? Well, the R is in fact what the symbol for correlation, right? When we're talking about ANOVA, it's the F. It's the F ratio, or as we call it, the F statistic, that's defining the ANOVA. Okay, this won't surprise anybody. The calculated F ratio is compared with a critical value for statistical significance. Again, every time we've had inferential statistics, this has been the case. For ANOVA analysis, we look at the variability among and within samples. I'll get to that in a few minutes. Okay, But for now, I just want you to concentrate on understanding that an ANOVA is something that you're going to use instead of a t-test if you have more than two populations or samples that you're comparing. Okay, that's the main thing to remember here. And finally, the null hypothesis states there is no difference between the means of each sample or population. Okay, so that's how the null hypothesis will read for a ANOVA. You can kind of see here as a visual aid, okay, an ANOVA, okay, we have a population 1, see that's mu1, okay, mu2, mu3, mu4. Clearly, if we're testing this many mu's, we're going to be using ANOVA, not a t-test. So I have for you a little bit of an illustration here as to why we use ANOVAs instead of separate t-tests. And the first thing that you might notice is the illustrations I have before you are things you recognize. We have three populations here, three independent populations, and we also have samples taken from each population. So you might be automatically thinking, as would be the case incorrectly, in other words, it would be absolutely correct for you to think, wow, this looks an awful lot like a independent samples t-test. It does indeed look like that. But here's the problem with believing that you can run multiple t-tests and make similar comparisons. Let's take a look here. If we ran a t-test, and let's just call each one of these averages, these are all the populations of people on different continents who have, let's just say, in this case, diabetes. So we're going to say the population of folks who suffer from diabetes in North America. Okay. And keep the colors consistent. South America. Finally, Asia. Okay. I could go on. I mean, we could have had another one, Africa. We could have done India. We could have done a lot of things here. Although I think the Indian subcontinent is also considered part of Asia. But nonetheless, I digress. So here's what we're going to say here. If you were thinking, well, these look like independent populations with samples, therefore we should probably be able to run a t-test, I would say this to you. Let me just switch it up here. Okay, if we ran a t-test between these two populations, okay, what is the p-value that we come to that is the highest allowable p-value where we can still reject the null hypothesis? You know the answer. The answer is you can have a p-value of equal to or less than 0.05. Okay. All right. So effectively 5%. We can get it wrong 5% of the time and still be okay with rejecting the null hypothesis. Okay. Now, somebody says, well, great, we could set this up as a t-test, and then we could run another t-test between these two populations. Here's what gets problematic. The same thing here applies here. So what have you done here? You've basically said, okay, now in order to reject the null hypothesis, we can go out to 0.05 plus 0.05, or what would that be? Okay, 0.10, okay? That's not going to work, okay? Because we said from the beginning that if you have a p-value of greater than 0.05, you must accept the null hypothesis. But if you're doing more than one t-test, you're automatically building in this, okay? Because each t-test can go up to 0.05. So the problem with, again, a series of t-tests is you're increasing the probability that you're going to get a higher p-value than you want to allow. That's not going to work. So a ANOVA says, we're not going to do this. We're going to just do one test. So I'm gonna back this out a little bit and show you what this looks like. Isn't this neat function? I love this thing. Here's what an oops, let me come back up here. Here's what an ANOVA says. Okay, an ANOVA says, no, we're going to compare all of these. Oops, all of these. Let me do that again. Goodness gracious. Isn't this a wonderful function? I can take care of all my mistakes. Okay, we're going to compare all of these, but we're going to keep it at a level of 0.05 in terms of the p-value. In fact, we could have a bunch more populations. We could have said North America, South America, Asia. We could have said Iceland. We could have thrown in a lot of different other places. Europe. Okay, and we're still going to keep it at 0.05. So it's much more stable. And those quotes that I gave you initially were exactly what we were trying to say here. We were trying to say that instead of running multiple t-tests, if you run one ANOVA, you're going to have a safer ballpark to play in because you're not going to run the risk of increasing the allowable p-value, okay, by doing multiple t-tests. I know that's a little hard to grasp, but the main take-home here is the reason we would use an ANOVA instead of a series of t-tests is because your results are more stable. We're going to be able to get, again, stick with the same thing we've been doing for the last several months, allow only a p-value of up to 0.05, okay? Or in other words, have a 0.05 cutoff, okay, in terms of deciding whether to accept or reject the null hypothesis. Otherwise, with multiple t-tests, you're really mucking up the waters. It's making it much harder to stay consistent with this standard. Okay. So now I've returned to my PowerPoint for you after I kind of took a little bit of a detour to give you an illustration. Coming back up to this is a example of research. Here's a table. This has to do with numbers of combined tardies and unexcused absences. And I want you to notice this is at 3 different schools: School A, School B, and School C. Now, in case you hadn't noticed, which I'm pretty sure you have, just like t-test, we're looking for averages. We're comparing averages. That was even in the first introductory quote, was talking about averages. So again, this is another reason why ANOVA and t-test are very similar, is again, we're looking at averages. So what do we have here? We have teachers at these schools. We have 15 teachers from School A, from School B, from School C, and they're all recording. They're recording the number of combined tardies and unexcused absences. Now, the null hypothesis for a ANOVA under these circumstances would say there's no difference between these averages at all. But to test it out, here's what they did. They went ahead, and you can see the way they've done this, just something like I might teach you. Okay, they took all the data, okay, crunched it at the bottom, sigma x. So sigma x is going to be, you added all this up, 46, okay? And then of course, if you see the bar, x bar for School A, okay, we're going to go ahead and take 46 rather, divide it by 15 to get the average. So the average here is 3.07. Same mechanics applied here for School B. We added everything up, so sigma x for School B is 34. We divided it by 15 to find the average. So there's the x bar for our second school. Okay, 2.27. There's your average. Okay, School C, we did the same thing. Okay, added them all up. We have the sigma x is 40. Okay, again, divided the 40 by 15. Okay, that's going to give us an average as well. Okay, as you can see, we have 3 averages here for 3 different schools: 3.07, 2.27, 2.67. So this would be like an example you might see in real life of somebody running an ANOVA. So if you followed me this far, you probably might be saying, well, I understand conceptually what an ANOVA is about, but what about the formula? And the formula turns out to be something unlike anything we've seen in the class so far. It looks like this. You have the F-score, F. It's also called the F ratio, and here's why. We have MS between over MS within. And remember earlier in the presentation, I talked about how the F score can also be called the F ratio. That's pretty accurate. Now you might be saying, what's MS stand for? Is that Microsoft? No, it's nothing like that. I'm going to back up one screen. Okay, it's the mean squares. Okay, how do you find these? Well, here's how it is. You're going to take the sum of squares between, okay, the groups, and you're going to divide that by the degrees of freedom between. And for the within, you're going to do the same thing. You're going to take the sum of squares within a group and divide it by the degrees of freedom within. I'm not going to spend a tremendous amount of time on this because you're never going to do any of these calculations. I just want you to see what they look like so you have some familiarity with them. But again, what we're going to probably do to help you the most is to go on to look at one more example. Okay, and now we have a simple example of an ANOVA analysis. Take a look at this picture here. Looks like a stressful test, although looks like they have good social distance, huh? Okay. I think this was taken long before the issue we're in now, but nonetheless, this is an example of a ANOVA analysis. Let's take a look at the fact pattern. Okay, when I push the button, okay, here it is. A research study seeks to learn the impact of varying levels of anxiety on test scores. Okay, so it looks to me like we've got two variables here, test scores, and we've got levels of anxiety. Okay, so let's take a look at how they set this up. The null hypothesis is there is no difference in the means of samples of varying anxiety levels and test scores. So again, think about that really quickly. No difference in the means. Okay, sounds an awful lot like a t-test. The varying anxiety levels and test scores. So again, there's your two variables, but we don't know exactly how many levels of anxiety, and that's really the key here. The study set up three categories of anxiety: high, medium, and low. So now we've got three. Kind of takes us out of the realm of t-tests and moves us more into ANOVA, which is exactly what was used. Okay, 10 participants are randomly assigned to each of these groups. So we've got 10 folks in high, 10 folks in medium, 10 folks in low. And then what the researchers do, participants are then subjected to corresponding levels of anxiety as they take tests, high, medium, and low. And the question is, did the anxiety have any impact on the test scores statistically? Was there a statistical difference between the three test score categories, and with respect to the anxiety? Okay, the scores for each group are compared for variability within and among the different groups. That's exactly what you saw in the previous slides when we were looking at the formula between and within. Okay, the groups, we're looking for variability. How much is changing within, how much is changing between the groups. That's how you measure with the ANOVAs. Okay, so here's what ended up happening in this particular case. And a lot of times if you're going to read an ANOVA readout or output from SPSS, which is a lot of time what you see, okay, it's going to look a lot like this. You can see on the far left things that are predictable between and within. We went over that earlier. Okay, sum of squares. Okay, degrees of freedom. Remember, you would say that the sum of squares between divided by the degrees of freedom. Okay, it's going to give you the mean square. Okay, then we have the within, same drill. Okay, and then when we find the ratio, it was 2.04. Okay, that was the F score. You can see that right there, and you can see the p-value. It says that the p-value was greater than 0.05. So you really can read this whole. This is one of those things that students may have skipped in the past when they were reading a study. They were like, okay, well, let me just read the paragraph. That chart I don't understand. Well, now you can understand the chart. Now you can understand what the chart means as a result, hopefully, of taking this class. Okay, so ultimately, after performing all computations, the researcher determined an F ratio of 2.04. Again, can be called an F ratio, might be called a F score. In any case, that's exactly what we're talking about. As an ANOVA output is going to be called a F ratio, F statistic, F score. Okay. When comparing it to the critical value, which I didn't have listed here, but it didn't really matter because we knew about the p-value anyway. Okay.
obviously the critical is going to be larger if the p-value was greater than 0.05. Thus the null was accepted. So what was the outcome? There is no difference. There really is no difference between, statistically speaking, test scores from students taking it under the conditions of high, medium, and low levels of anxiety. Okay, so again, we're not running a lot of analysis here. I'm just trying to get you to wrap your heads around what all this means, so that when you come across it in a study, or when in the future you have a future class, and you're talking about comparing averages among samples, and there's more than two, you know that an ANOVA is what's appropriate. So again, we're not trying to cram too much here at the end. It's more just me trying to add some value to the course. So anyway, hope this was somewhat clear, and I'm going to go ahead and put a participation quiz up for today, which again will be just for the purposes of attendance. Okay, and we'll see each other again on Monday.